Today, are you able to view the screen, everyone? Are you able to view the screen?
Yes.
Okay, so there are some properties of convolution which you have to know. Okay, they might ask you properties of convolution also. So the first property which we are going to discuss is commutative property. So commutative property of commutative property holds good for convolution sum and convolution integral both. Okay. So let us see convolution property for commutative property for convolution sum. Later we shall see for convolution integral. Okay. So for convolution sum, it states that x of n convolved with h of n is equal to h of n convolved with x of n. Okay. So we shall try to prove the LHS and RHS, and we have used this in problems also, right? Many problems in convolution sum. So we shall try to prove. So we have, if you have x of n convolved with h of n, so it's equal to h of n convolved with x of n. So we'll try to take the LHS and try to prove the RHS. Okay. So we'll take the LHS, which is x of n convolved with h of n. So what is the equation for convolution sum? You have summation k is equal to minus infinity to infinity x of k into h of n minus k. Okay. So what we are trying to do is we are taking LHS and trying to prove RHS. So this is the equation for, if we take the LHS, this is the equation for convolution sum. Now I'll replace this n minus k with m. Okay. N minus k is equal to m. So if you are trying to replace n minus k is equal to m, when k is equal to minus infinity, what is the value of m? When k is minus infinity, what is the value of m? N minus of minus infinity, what do you get? When k is minus infinity, lower limit, what is your m? N minus of minus infinity, what do you get?
Infinity.
Plus infinity, right? So it will be plus infinity. When k is equal to infinity, what is m?
Minus infinity.
Minus infinity, right? So our limit of summation would be m is equal to infinity to minus infinity. Okay. X of what is k? N minus k is equal to m. So k is equal to n minus m. Correct? Yes or no? N minus k is equal to m. So what is k? K is n minus m. Okay. So in place of k, I'll replace n minus m into h of m. So we know that in summation we can change the limits without changing the sign, right? So I'll change the limits from minus infinity to infinity. M. Okay. So the summation would be m is equal to minus infinity to infinity h of m into x of n minus m. Okay. So as you can see here, we have x of k into h of n minus k. We have x of n convolved with h of n. So here we have summation m is equal to minus infinity to infinity h of m into x of n minus m. So what is this equal to? We can write it as h of n convolved with x of n. So it is h of n convolved with x of n. So this is your RHS. Hence your convolution sum is proved for commutative property, or commutative property is proved for convolution sum. Got it, everyone? Clear?
Yes, ma'am.
So I explain you once again. Please listen. If commutative property states that if you convolve x of n with h of n, it is same as convolving h of n with x of n. Okay, if this is first and this is second, next if we take this second term first and the first term second also, it's the same. Okay. So LHS is x of n convolved with h of n. So this is the convolution sum because it is discrete time signals, right? So it's convolution sum. So the convolution sum of x of n converted with h of n is summation k is equal to minus infinity to infinity x of k into h of n minus k. So in this equation, I'll take n minus k and I'll replace it with m. Okay, I'll take n minus k and replace with m. So when lower limit is minus infinity, what happens to m? You have n minus of minus infinity. So it will become plus infinity. M is plus infinity. Okay. Next, if k is equal to infinity, what happens to lower limit, upper limit? If k is infinity, n minus infinity will be m is equal to minus infinity only. Okay, n is some value. If you subtract n from minus infinity, it will be minus infinity only, right? So you have upper limit and lower limit as infinity and minus infinity. So m is equal to summation of m is equal to infinity to minus infinity x of n minus m. How we got n minus m? Because in place of we are n minus k is equal to m. This we have taken the equation. So k is equal to n minus m. Putting this here and putting this here. Okay. So k is n minus m into h of m because we are replacing n minus k with m. So I can interchange the limits in summation without a negative sign. So I have summation m is equal to minus infinity to infinity h of m into x of n minus m. As you can see, this equation represents the convolution sum, right? So it's nothing but h of n convolved with x of n. So our RHS is proved. Got it, everyone? Is it clear?
Yes, ma'am.
So now let us try to prove commutative property for convolution integral. Okay. So in convolution integral, we have continuous time signals. Okay. So convolution integral is for continuous time signals. So we have x of t convolved with h of t is equal to h of t convolved with x of t. So we'll try to prove this. We'll take similarly like convolution sum only we'll do. We'll take LHS and try to prove the RHS. Okay. So what is LHS? It is x of t convolved with h of t. So commutative property states that x of t convolved with h of t is equal to h of t convolved with x of t. I am taking LHS and trying to prove the RHS. So LHS is x of t convolved with h of t. So what is the equation for convolution integral? So we have tau, which is equal to integral minus infinity to infinity x of tau into h of t minus tau into d tau. Okay, tau is equal to minus infinity to infinity. Okay, this is the equation for convolution integral. So what I'll do is I'll take t minus tau as m. Okay, if you take t minus tau as m, so m is some new variable which I'm equating t minus tau to. So when tau is equal to minus infinity, what is m? When tau is equal to minus infinity, what is the value of m?
Plus infinity.
Plus infinity.
Plus infinity. When tau is equal to infinity, what is m?
Minus infinity.
M is equal to minus infinity because we'll have if tau is minus infinity, you have t minus of minus infinity, that will be plus infinity. So when tau is infinity, t minus infinity, it will be equal to m. So it will be m is equal to minus infinity. Okay. So we have 1 minute. So let us take this. I'll take equation for tau. Tau will be equal to t minus m. Okay, for replacing it here, and I'll differentiate with respect to this expression with respect to tau. If I differentiate this in place of d tau, what should we do? What should we put? We'll get to know. Okay, so if I differentiate this expression with respect to tau, so if I differentiate t with respect to tau, t is a constant. Okay, so it will be 0 minus. If I differentiate tau with respect to d tau, I'll get 1. So if I differentiate m with respect to d tau, I'll get dm by d tau. Okay, so you can write dm is equal to minus d tau, or d tau is equal to minus dm, which is equal to d tau is equal to minus dm. Okay, so now we'll try to replace the terms in this equation. So we have taken t minus tau is some equal to some new variable m. So we have integration limits for m now, which is equal to infinity to minus infinity, right? M is equal to infinity to m is equal to minus infinity x of tau equation. Tau is equal to t minus m from this. Okay, t minus tau is equal to m, and tau is nothing but t minus m. Okay, x of t minus m into h of m into minus dm. Okay, d tau is replaced with minus dm. Got it, everyone? Clear? Is it clear till here, everyone?
Yes, ma'am.
Okay. Now I want the limits from minus infinity to infinity. In integral, if you change the limits, you'll have to have a negative sign, right? So I have minus infinity to infinity x of t minus m into h of m into dm. So this minus and minus, it will become plus. So you have what is this equation? This equation represents the convolution integral, right? So I can write integral minus infinity to infinity h of m into x of t minus m dm. So the limit, the integration limits is on m, and you have h of m into x of t minus m. So I can write this as y of t, which is equal to h of t convolved with x of t. Got it, everyone? So if I change the limits of this definite integral, then I'll have a negative sign. Okay, here we have from infinity to minus infinity. I'm taking from minus infinity to infinity. I have a negative sign here. I'll have a negative sign. That will become positive with this negative sign. Okay, so have plus here. Got it, everyone? It's clear?
Yes,
It's clear or not? So we have taken LHS and trying to prove RHS. So LHS is x of t convolved with h of t. So you have integration limits from tau is equal to minus infinity to infinity x of tau into h of t minus tau into d tau. So what are we doing is similar to our previous convolution sum. We are trying to make this t minus tau is equal to m, which is equal to some new variable. So t minus tau is equal to m. So when tau is equal to minus infinity, m becomes infinity. When tau is equal to infinity, m will become minus infinity. Okay. So next, I'll try to differentiate this expression with respect to tau. So this expression t minus tau is equal to m. So t is a constant with respect to tau. So it will become 0. If you differentiate tau with respect to d tau, you get 1. So 0 minus 1 is equal to dm by d tau. If you differentiate d tau with respect to, if you differentiate m with respect to tau, you get dm by d tau. Okay. So we can write dm is equal to minus d tau, or d tau is equal to minus dm. In place of d tau, we have to put minus dm. Okay. So now we have got our limits. M is equal to infinity to minus infinity. X of tau is equal to t minus m. Got it? X of t minus m into h of m into minus dm. Okay. So I want to change the limits of integration. So I will have a negative sign here. Okay. So that negative sign will get balanced with this negative sign, and we get positive. So integration minus infinity to infinity x of t minus m into h of m into dm. So this I can write it as integral minus infinity to infinity h of m. So limits of integration is m. Okay. So integration limits minus infinity to infinity h of m into x of t minus m into dm, which is nothing but h of t convolved with x of t. Got it, everyone? Is it clear?
yes, ma'am.
Understood, everyone? So that is our RHS, and commutative property is proved for convolution sum as well as convolution integral. So now let us see distributive property of convolution. Distributive property of convolution. So So this states that x of n convolved with h1 of n convolution, yes, x of n convolved with h1 of n convolved with h2 of n is equal to x of n convolved with h1 of n plus x of n convolved with h2 of n. This is the distributive property for convolution. Okay, this is for discrete time signals. So you have x of n convolved with h1 of n convolved with h2 of n is equal to x of n convolved with h1 of n plus x of n convolved with h2 of n. This is plus here. Okay, so x of n convolved with h1 of n plus h2 of n is equal to x of n convolved with h1 of n plus x of n convolved with h2 of n. Okay, this is a distributive property of convolution. So you consider interconnection of systems. Okay, we haven't done interconnection of systems. So we shall do with properties, along with properties, and we'll solve problems on interconnection of systems. So if you consider an interconnection of systems, so you're trying to give x of n to two systems, that is h1 of n as well as h2 of n. Okay, what is the output? What you get here? X of n is given to two systems, h1 of n, h2 of n. Okay, so systems are having impulse responses h1 of n, h2 of n. Okay, so y1 of n is the output from h1 of n, and y2 of n is the output from h2 of n by giving x of n as the input. So you get y1 of n plus y2 of n. So if we add it, so that will be equal to y of n. Okay, so y of n is equal to y1 of n plus y2 of n. So this is the systems in parallel. Okay, so if you have a systems in parallel, you can replace it with h1 of n plus h2 of n. Okay, so x of n is given to two systems with impulse responses h1 of n, h2 of n, and y1 of n is the output from h1 of n, and y2 of n is the output from h2 of n when the x of n is given as input to both the systems. Okay, now we'll take what is y1 of n. So it is similar to our LTI system. If you give x of n to the system with having impulse response h of n, you get output y of n. So what is y of n? Y of n is a convolution of x of n convolved with h of n, right? So it is same to that. So we'll take what is y1 of n. So y1 of n is output from h1 of n when input is given as x of n. So y1 of n, I can write it as x of n convolved with h1 of n. Okay. Similarly, I can write y2 of n as x of n convolved with h2 of n. Okay. So our y of n will be the summation of y1 of n plus y2 of n. Okay. So we are taking RHS and trying to prove LHS. Okay. So our RHS would be this one, y1 of n, which is equal to y of n is equal to y1 of n plus y2 of n. So I can write y of n as x of n convolved with h1 of n plus x of n convolved with h2 of n. Okay, so we have got the RHS. So this is the RHS. So we are taking the RHS and trying to prove LHS. So you take summation. So this is the convolution sum, right? Because we have discrete signals, x of n convolved with h1 of n. We can write it in terms of convolution sum as summation k is equal to minus infinity to infinity x of k into h1 of n minus k. Okay. Similarly, we can write this x of n convolved with h2 of n as summation k is equal to minus infinity to infinity x of k into h2 of n minus k. Okay, so now if I take common terms in this, so I'll have summation k is equal to minus infinity to infinity x of k into h1 of n minus k plus h2 of n minus k. Okay, which is equal to, so I can write it as x of n, which is convolved with h1 of n plus h2 of n. Got it, everyone? This is our LHS. So this is the proof for distributive property using convolution used for discrete time signals. Understood, everyone? So if you have systems in parallel like this h1 of n, h2 of n, you can write h1 of n plus h2 of n. Okay. So this is some interconnection of systems property. So you have systems in cascade and systems in parallel. So distributive property is nothing but interconnection of systems in parallel. Okay, if you're having x of n as input, you're giving it to the two systems having impulse responses h1 of n, h2 of n, then this output would be y1 of n, which is nothing but output of h1 output when the impulse response is h1 of n and when the input is x of n. Okay, y2 of n is the output when the impulse response is h2 of n and when the input x of n is given. Okay, so if we add that y1 of n, y2 of n, we get y of n. Okay, so distributive property states that x of n convolved with h1 of n plus h2 of n is equal to x of n convolved with h1 of n plus x of n convolved with h2 of n. Okay, so we are trying to take RHS. What is RHS? X of n plus x of n convolved with h1 of n plus x of n convolved with h2 of n. So y1 of n is x of n convolved with h1 of n, y2 of n is x of n convolved with h2 of n. So this is y1 of n, y2 of n. So y of n is summation of these two, y1 of n, y2 of n. So y of n is equal to y1 of n, y2 of n. Write this in terms of these x of n and h of n. So y of n is equal to x of n convolved with h1 of n plus y2 of n is x of n convolved with h2 of n. Write in terms of convolution sum both of them. Then take the common terms. What is common? Summation is common and x of k is common. Take them common and write h1 of n minus k plus h2 of n minus k. So which is nothing but our LHS x of n convolved with h1 of n plus h2 of n. Clear, everyone? Is it clear? It's clear or not?
Yes, ma'am.
Understood, everyone?
Yes, ma'am. Yes,
So now the conclusion from this distributive property is if two systems are in parallel with impulse response h1 of n and h2 of n, then you can write it as h1 of n plus h2 of n. Okay, you have two systems in parallel with impulse responses h1 of n and h2 of n. Okay, and if we add it, we get y of n. Okay, so if we have like two parallel impulse responses, so we can write it as x of n, which is equal to, x of n. If you give it as input, you can replace two systems in parallel as h1 of n plus h2 of n. This is important for interconnection of systems. Okay, so you get y of n. So this holds good when the systems is parallel and you have positive sign here. Okay, if you have negative sign here, if you have plus and minus, what happens? So x of n would be, if you're giving x of n as input, so it will be h1 of n minus h2 of n, which is equal to y of n. Got it, everyone? Check the signs also here. If both are positive, you get h1 of n plus h2 of n. You are reducing the system to h1 of n plus h2 of n. If this is positive, this is negative, then you are reducing this to h1 of n minus h2 of n. Got it, everyone? Clear?
Yes, ma'am.
So this holds good for convolution integral also, or continuous time systems also. So if you are giving x of t as the input two systems in parallel, that is H1 of t as well as H2 of t, then if you are adding them both, then you get y of t. So if you have two systems in parallel, then you can add them up. Okay, so you can replace this parallel systems by H1 of t plus H2 of t. Got it, everyone? It depends on this sign also, which we are given here. If you have both positive, it will be H1 of n, H1 of t plus H2 of t. If you have negative here, it will be H1 of t minus H2 of t. If you have negative here and positive here, it will be minus H1 of t plus H2 of t. Got it, everyone?
Ma'am, this property holds for only convolution systems, ma'am.
Yeah, for convolution sum and convolution integral, this distributive property holds good.
No, ma'am. If some systems like if we give input as x of t, output is x of t minus 2, for that systems also this property holds, ma'am.
This is LTI systems, no? You have impulse response. Y of t is equal to x of t convolved with h of t, or your y of n is equal to x of n convolved with h of n. Right? What is this? H of t and h of n. Impulse response systems, right?
Yes, ma'am.
So what is impulse response? If you are giving x of n to the LTI system, you are getting output y of n. What if you give delta n, impulse signal, delta n or delta t? You have to get the impulse response, that is h of n or h of t. Got it? So what do you conclude? So if x of n is given to the system having impulse response h of n, so output will be y of n, which is nothing but y of n is equal to x of n convolved with h of n. Got it? Or y of t is equal to x of t convolved with h of t. Clear?
Yes, ma'am.
Okay, so this is for convolution property. The distributive property holds good. Okay, for convolution integral as well as convolution sum. So you try to prove this for continuous time signals, distributive property. Okay, it's the same thing. You try to prove, you will get it. So if you have, so this is systems in parallel. Okay, if you have two systems in series, we shall see how it will be. So if you have x of n and you have h1 of n in series or cascade, we can call it as cascade also, h2 of n. If you have like this, you can write this as h of n is nothing but h1 of n convolution h2 of n. You can replace this h1 of n and h2 of n as h1 of n convolution h2 of n. Okay, if systems are in series. If two systems h1 of n and h2 of n are in series, you can replace h of n as h1 of n convolved with h2 of n. If the two systems are in parallel, you can replace, I am giving x of n to both the systems in parallel, h1 of n and h2 of n. So you get y of n. So h of n in the parallel case would be h1 of n plus h2 of n, plus or minus depending on the signs here. Okay, got it? If two systems are in parallel, then h of n would be h1 of n plus or minus h2 of n. If they are in series or cascade, it will be h1 of n convolved with h2 of n. Got it? Is it clear?
Yes, ma'am.
Okay, so let us now see associative property of convolution. Associative property of convolution. Understood distributive property, everyone? So associative property of convolution states that x of n convolved with h1 of n convolved with h2 of n is equal to x of n Are you guys able to hear me?
Yes, ma'am. Now we can.
Okay. Screen. You're not able to hear me?
Ma'am, your voice is
Voice is
breaking.
breaking, ma'am.
It's audible now?
Yes, ma'am.
You're able to view. Okay, lost the connection. Guys, am I audible now?
Yes, ma'am.
Okay. Everyone, are you able to view the screen? Present now?
No, ma'am, can't see the screen.
It was fine. Now we are able to see the screen. Are you able to see the screen, everyone?
Yes, ma'am, we can see.
Okay. So we'll try to work the associative property now. Now are you able to view the screen? This screen?
Yes, ma'am.
Okay. So associative property. Convolution. So it states that if x of n convolved with h1 of n convolved with h2 of n is same as x of n convolved with h1 of n convolved with h2 of n. If this bracket is replaced here. Okay. So first I'm putting the bracket to the first two terms. X of n convolved with h1 of n convolved with h2 of n is equal to x of n convolved with h1 of n convolved to h2 of n. If I put the bracket to the next two terms. So this is same. So this is the associative property of convolution. So now let us take this as f1 of n. Okay, and this as f2 of n. Okay. So what is f1 of n? What is f1 of n? What is f1 of n? It's x of n converted with h1 of n,
Yeah,
right?
ma'am.
So x of n
Yes, ma'am.
converted with h of n. So I can write it as summation and take some variable m. M is equal to minus infinity to infinity x of m into h1 of n minus m. So h1 of n. Okay. So now I'll take f2 of n. So f2 of n is equal to h1 of n convolved with h2 of n. So I can write it as summation and take some r. So r is equal to minus infinity to infinity h1 of r into h2 of n minus r. Got it, everyone? Here is clear.
Yes, ma'am.
It's clear. Okay. So I'll take LHS and try to prove RHS now. Okay, we'll take LHS and I'll try to prove this one. So observe here, what is our LHS? It is LHS is equal to x of n convolved